Hi folks! In this video we're going to look at some problems that involve motion in a straight line just in one dimension. So in the last video we had some definitions, we had some examples to just understand what this looks like. Here we're looking at a particle that moves along a straight line, so it's just going to move left to right. And it's given by this really contrived equation here. That's its life story. It just does that. Where S is in centimeters, so S stands for position, and T is in seconds. So we can find the position when T equals 0, and the position when T equals 3. So if I put 0 in for S, or for T rather, I'm going to get 0 squared minus 4 times 0 plus 3. And that's going to give me 3. If I put in 3, I'll get 3 squared minus 4 times 3 plus 3. And that's actually going to give me 0. Okay. So in context, when T equals 0, we're 3 centimeters right of the origin. When T equals 3, we're at the origin, or on the origin. So maybe I'll just make a little motion diagram of what I know so far. Here's the origin, okay, and this is in centimeters. And here's where the particle's born, right here, at T equals 0. It's 3 centimeters right. And then I also know on its 3rd birthday, it's right here at the origin. Now, I actually don't know a whole lot about what happens around there. And I'm going to try and use as much space as I can on this particular slide so that I can keep it together, but these tend to be big problems. Find the average velocity over the first 3 seconds. Well, let's see. Average velocity is going to be change in position over change in time. And it's always final minus initial. So the final position is 0. The initial position is 3. The final time that we're talking about would be 3. And the initial time that we're talking about is 1, or is 0 rather. Now, again, finding slope doesn't make a whole lot of sense if we don't give it some meaning with units, so centimeters and seconds. So the average velocity is negative 3 centimeters in 3 seconds, or negative 1 centimeters per second. Does that make sense? Well, over those first 3 seconds, it went an overall displacement of 3 centimeters to the left. Does that tell us the velocity at every instant? Heck no. So velocity over those first 3 seconds on average was negative 1 meter per second. And now I think I need to have a little more space to do the rest of this. For part C, it says, find the velocity when T equals 3. This is instantaneous velocity. So what is going on exactly at that moment? Well, we'd have to differentiate. So the first derivative of position is velocity. So that would give us 2t minus 4. And velocity at 3 would be 2 times 3 minus 4, or 2. And this is in centimeters per second. Now let's assign that some meaning. What that's saying is when t equals 2, or t equals 3 rather, the particle is moving rightward because it's positive, rightward or forward, at a rate, it's a derivative, so we're always going to use those magic words, at a rate of 2 centimeters per second. You might say, well, hold on, how can that be? It looks like it had moved left. Let's tell some more of the story. At what time does the particle reverse directions? So in order for something to turn around, for it to reverse directions, it momentarily has to have a velocity of 0. Let's write that down. In order to turn around, we must momentarily have a velocity of 0. It could be for more than a moment. Another thing to note here is if you have a velocity of 0, it doesn't guarantee that you turn around, but this is a necessary, though perhaps not sufficient condition. So velocity for us is 2t minus 4. Where is that going to be 0? It's going to be 0 at t equals 2. Now, some people might want to find that just by kind of factoring this one out and saying, oh, what would 0 it out? Okay. So that's where you have a velocity of 0. What I'm going to do is I'm going to make a little number line here that's going to talk about velocity and the direction that we're going. So at around time equals 2. Okay. And this all starts at t equals 0. What if I put a number that's between 0 and 2 into the velocity function? Okay, what if I put in the number 1? Well, I'd get a negative velocity. And a negative velocity would mean that it starts by moving to the left. What if I put in a number bigger than 2? Like let's put in 3 into this velocity function. That would give us 2 times 3 minus 4. Well, that would give us a positive number. And that would tell us, because velocity is positive, we'd be moving to the right. So if you change from moving left to moving right, you must have turned around. Okay? We turn around when t equals 2. And you might say, well, we kind of knew that over here at this point. But actually, we needed to show that it does turn around with this little sign diagram. Next, it says, what is the position when the particle changes direction? So we know when it happens. Where does it happen? Well, you'll have to throw it in the original function. You'll have to find s at 2. Okay? And s of t was t squared minus 4t plus 3. So we'll have 2 squared minus 4 times 2 plus 3. And that's going to give us, what, 4 minus 8 plus 3, or negative 1. It turns around 1 centimeter left of the origin. Okay, that's what a negative position means. Now the next thing that it asks is to draw a motion diagram. So I actually started that up here, but let's do a better version down here. In the little sign diagram above, all my sort of x-axis, those were just times. But here in my motion diagram, I want to show positions. So here is the deal with this setup. We already know that when time is 0, its position is 3 centimeters to the right of the origin. That was the first thing that we found in this. Okay? S at 0 is 3, right here. We also happen to know that when time is 3, it's at the origin. But actually more important than that is that when time is 2, it's right here. It's at negative 1. Now I'm going to show this as sort of snaking around upwards, but there's actually no upwards motion. What this particle really does is it goes left, and then it goes right forever. Okay? But that's hard to show without having any sort of motion up and down to represent it. So here's what's going on with this particle. It heads to the left, okay, and that's what this velocity here being negative shows. Heads to the left up until its second birthday when t is 2. It heads to the right then. T is 3. It ends up right here. And we actually already know that it goes on forever like this. That's the whole life of this particle. Just keeps going to the right forever and ever. The last two questions that this question asks are, what are the net displacement and the total distance traveled? So displacement is just the change in position. Okay. So it says over the first 3 seconds. Let's look at the question. Find the displacement and total distance traveled over the first 3 seconds. So that would just be s at 3 minus s of 0. Okay, final minus initial. And s at 3 we found in the very first question. S of 3 is 0. It's right over here. It's kind of grayed out there. And s of 0 is 3. So this is going to be 0 minus 3, or negative 3 centimeters. Does that make sense? If you think about where this particle started and where it ended up after 3 seconds, yeah, it went 3 centimeters to the left, so displacement of negative 3. On the other hand, if you want to know its total distance traveled, that's a little trickier. It made 4 centimeters worth of sort of distance here, and another 1 centimeters. So it's going to be 4 centimeters plus 1 centimeter. Total distance traveled over the first 3 seconds is 5 centimeters. And that distance has to be positive. We never talk about negative distance. We do talk about negative displacement, though, because displacement is net change in position. Let's do another one where we have a cubic to work with. So we've got the same sort of setup. This time it's in meters. Time has to be positive or 0. And it asks us for the velocity at t equals 2 and t equals 4. That word at lets us know that it is instantaneous velocity. So velocity is the first derivative of position, which would be 3t squared minus 12t plus 9. Now, that's factorable, so I would be inclined to factor it because it is going to be helpful later on, depending on what we're trying to do. So sometimes the sort of expanded form will help, sometimes the factored form. Okay. Find the velocity at t equals 2 and t equals 4, so let's just plug that in. Velocity at 2 would be 3 times 2 squared minus 12 times 2 plus 9. Might have been easier to figure it out from the factored form, but v of 2 is going to be negative 3, and we're talking about meters per second here. On the other hand, if we want v of 4, well, that's going to be 3 times 4 squared. Let me do this one from the factored form. Let's see if that's easier. 3 times 4 minus 3, that's 1. Times 4 minus 1, that's 3. Oh, yeah, that is easier. 9 meters per second. Okay. So just to be clear, at this point here, it's moving leftward because velocity is negative. We're moving backward. Here, velocity is positive, so we're moving forward or rightward. When is the particle at rest? So the factored form actually really helps us see that. When is velocity going to be 0? It's going to be 0 at t equals 3 and t equals 1. When is the particle moving forward? This is another one of those cases where we'll want to make a sign diagram for velocity. So it can only change from moving forward or backwards at these 2 points here, or those 2 times, t equals 1 and t equals 3. Okay. And it starts its life at t equals 0. Velocity we already found in factored form is t minus 3 by t minus 1. Okay. So what if we put in some values in here? Let's see. It's something between 0 and 1. What if we had put in 0.5 here? 0.5 for t. I just want to find out what velocity is going to be. And I don't actually want to figure this out. I just want to say it's going to be 3 times a negative number times a negative number. Velocity is going to start off positive, which means we're moving forward. So I guess part of the answer to this question is we're moving forward in the first 1 second. Forward. Let's see. What if I took the same idea and I put in a number for t between 1 and 3? Right? Probably put in 2. Let's see what happens then. So if I put in 2, I'd have 3 times 2 minus 3. And 2 minus 1, that would be 3 times a negative times a positive. Velocity would be negative, and we'd be moving backward. And lastly, if I put in something bigger than 3, say if I put in 4 for t, I can figure out what's happening with velocity then, which is the hack for knowing the direction it's moving. And clearly this is all just positives multiplied together. So it's moving forward at 3 and beyond. Now some books will include the 3, some won't. It doesn't really matter whether you include those endpoints or not. But the answer is it's moving forward in the first 1 second of its life, and then from the 3rd second onward. We need to draw a motion diagram. So to do that, we actually need to find the positions of the particle at all these important times. So we're going to have to find s of 0, s of 1, and s of 3. And here's the function here. If I put in 0, you can see I'm just going to get 0. If I put in 1, I'll get 1 minus 6 plus 9, so 4. And if I put in 3, I'll get 27 minus 54 plus 27. It'll be back to 0. Those are really the only important places in the life of this particle. So this is meters, 1 meter, 2 meters, 3 meters, 4 meters, and so on. So this particle is born at the origin. And then it moves right for a little while until it gets to 4 meters. And that happens on its first birthday. Okay, so that's moved right for a little while, just like this said. Now it's going to move left for a little while until it gets back to this position. And that happens on its 3rd birthday. So it's moved right, then left. Okay, that's this portion of its life. And then what does it do? It moves rightward forevermore. So there's question D. We could answer questions about displacement. Its displacement over the first 3 seconds, though, is 0. It ends up back where it started. Its distance over the first 3 seconds is 8 centimeters. At t equals 4 is the particle slowing down or speeding up. The easiest way to figure this out is to figure out what the velocity is at 4 and what the acceleration is at 4. If both of them have the same sign, then we're speeding up. Okay. Now, to figure out acceleration at 4, we're probably going to have to think about differentiating again. So let's see. The velocity function was 3t squared minus 12t plus 9. Okay. And that was s prime. Okay. S double prime is v prime, is the acceleration function, and that would be 6t minus 12. Okay. So if you plug 4 into the velocity function, I mean, we kind of already know it's going to be positive, but let's just do it for fun. You're going to get 9 meters per second. If you put 4 into the acceleration function, you're going to get 12 meters per second per second. Okay. Same sign. If velocity and acceleration have the same sign, we are speeding up. Okay. And that makes sense. That's kind of in this portion of the function's life, or the particle's life. It's going faster and faster off to the right. The next one's a little more opaque, though. It asks what is going on at t equals 1.5. Okay, so what would happen? V at 1.5 is going to be 3 times 1.5 all squared. This is probably easier from the factored form. Minus 12 times 1.5 plus 9. So let's see, that would be 3 times 2.25, that's 6.75, minus 18 plus 9. Honestly, I don't really care what the answer is. I do care whether it's positive or negative. It's going to be negative 2.25 meters per second. Okay. What about acceleration at 1.5? Well, that's going to be 6 times 1.5 minus 12, or negative 3 meters per second per second. Ooh, they're the same sign. So don't get weirded out that you got a negative acceleration. As long as we have the same sign between acceleration and velocity, we are speeding up. Now the last question is, find what time intervals when the particle is slowing down. And to do that, really you need to compare what's going on with velocity and what's going on with acceleration. So we know with velocity it starts being positive, then it's negative, then it's positive. We already made that sign diagram up here. For acceleration, so velocity, well, what's going on? Acceleration has this function. You could factor it if you want. It zeroes out at t equals 2. That's its important value. And anytime before you hit t equals 2 on this function, say if I put in 1 into it, so if I did a of 1, that's going to give me 6 minus 12. It'll give me negative 6. It's always going to be negative anytime that t is less than 2. If, on the other hand, we put in a number that is bigger than 2, say we put in 3, or 2.01, or whatever, it'll be positive. So I guess the question is, when are those signs between velocity and acceleration different? And it can help having tables right on top of each other, or sign diagrams right on top of each other, to notice, to start with right here, one's positive and the other one's negative. So from 0 to 1 second, you're slowing down. Now, what happens at 1 second? Well, at 1 second, then they both become negative. So speeding up. Not that this is what it asked us, but if we want all the times it's speeding up, definitely from 1 to 2 seconds that happens. Now let's check it out. At t equals 2, things change. Velocity's negative, but acceleration's positive. So you're going to be slowing down over that time. And then finally, in the end, you're going to be speeding up forevermore when t is greater than 3. Let's think about the motion of this particle. If it's going to turn around, yeah, it does have to slow down to hit that turn. And then after it turns, it'll probably speed up for a bit and then slow down to turn around again. And then it's going to speed up forevermore. So it kind of makes sense that it goes slow down, speed up, slow down, speed up. We'll come back for one last question on another short video. But if you're doing this from the IB Oxford textbook for Math AA SL, you can check out page 267 to 268, numbers 1 and 6. I hope this has been helpful. Good luck with the material, folks, and take care.